Welcome and thank you for joining me. In this lesson, we will learn how to define and determine the scalar, or otherwise called the Cartesian equation of a plane. Recall that so far we have defined the equations of planes in vector form, where x, y, z represents the coordinates of the head of any vector on the plane, equals x0, y0, z0, which represents the coordinates of the head of what we call the starting vector on the plane. You can think of this point as a fixed point on the plane, plus the sum of two direction vectors. And these direction vectors are what make the plane. And we take their scalar multiples, so respective scalar multiples, to accommodate any specific point on the plane. Now, based on the vector equation, we created the equations for each parameter, x, y, and z, or as we call them, parametric equations. And in this lesson, we're going to learn how to determine probably your most favorite equation of a plane, the scalar equation. It's very easy to find and very easy to implement in solving different problems. So let's get started. So in order to understand the scalar equation of the plane, we're going to look at a new way of envisioning the plane, or new elements in a plane. Or in other words, we're going to redefine the plane. Remember that a plane is a flat surface, and on a flat surface, you can draw as many perpendicular lines as you wish, an infinite number of perpendiculars. And those perpendiculars are what we call normal to a plane, and we actually talked about them when we visited lines and planes from the beginning of the unit. So, even though we draw many normals, you can imagine here that there is only going to be one normal that will cross the origin of the plane, so 0, 0, 0. And this is a special normal because it's the only one of its kind, and we call it the normal axis for the plane. And I'd invite you all to just try to envision the 3D axis, and drawing a line from 3D axis passing through the origin. There is only one way you can draw a perpendicular plane to it when you think about it. And that's why a normal is a perfect way to define a plane. We let the coordinates of any point on the normal be represented by letters capital A, capital B, and capital C. And we're going to say that the scalar equation of this plane will be ax plus by plus cz plus some constant d equals 0. Now, how does this work? In order for us to understand this, I want us to take a look at a very simple investigation. So this is the equation of a line in slope y-intercept form. And what we're going to do is determine the slope, which is 2 over 3. So we're going to say that the direction vector of this line will be the vector 3, 2. Remember that this is the x and this is the y coordinate of the direction vector. Now we'll convert this line into standard form. So we'll get rid of that fraction first, denominator 3. And now we'll take all the terms to the left side. And we'll change the coefficient of x. It has to be positive. So for this, you simply either divide by -1 or multiply by -1. So we're going to say that since we have the same line, right? So that would be both lines have the same slope, 2 over 3, and same direction vector, which is, in this case, 3 and 2. Now next, what we're going to do is find the slope of a line that is perpendicular to this one. So it's easier to look at the slope y-intercept form. So we're going to say slope perpendicular would be -3 over 2. So if you were to define the direction vector of the perpendicular to this line, then you will say that the direction vector must be 2, -3. So we'll say that for this equation, which is in standard form, and which I will box now because it's becoming a very important equation. So we're going to say that the slope of a perpendicular to this equation will be negative 3 over 2. And the direction vector of the perpendicular to this line then, as a result, will be 2 and negative 3. Now I want you to take a closer look at these two numbers, 2 and negative 3, which represent the coordinates of the perpendicular to this line, or the normal to this line. As you can see, they are right here, 2 and negative 3. So the coefficient of x is the first coordinate of the normal. The coefficient of y is the second coordinate of the normal. So guess what? If you were in 3D and you had an equation in the form ax plus by plus cz plus some constant d equals 0, then we'll say that the slope of the perpendicular to this would be equal to, now this obviously represents a plane, not just a line. So this would be equal to coordinate A, B, and then C. So that would be the direction vector. And this is the reason why, and this is how we describe or explain the connection between this equation and the coordinates of the normal to a plane. So now let's take a look at some examples, and I hope that we have established some, trust in the formula, that it works and it has some logical connection with the coordinates of the normal. So in example number 1, we are given the point A, 1, 2, 2, which is a point on the plane, and the normal is negative 1, 2, 6. We have to find the Cartesian equation of this plane. So in this case, in order to find the Cartesian equation of a plane means that we need to find something in the form ax plus by plus cz plus some constant d equals 0. Now, as you can see in here, we have the coordinates of the normal, which means that we have A, we have B, and then we have C. And we can easily substitute the values of A, B, and C in this equation. However, we do not know what the coefficient d is. And for this, we are going to use the coordinates of point A, which are 1, 2, 2. So these will be our x, y, and z values. So if you substitute, then you get negative 1, which is the value of A, times x, which is 1. I'm going to put the numbers here, actually, why not? So it's easier to follow them. And then 6. So we have 1 times 1. And then plus 2 times 2. Plus 6 times 2. Plus some constant d equals 0. So this is negative 1 and a 4 and a 12. Plus d equals 0. So that would equal 3 plus 12, 15. D must be negative 15. So therefore, we'll say that the equation of this plane in scalar or Cartesian form will be negative 1x plus 2y plus 6z minus 15 equals 0. And obviously, we would like to convert this to a positive number, so switch all the signs by multiplying by a negative or dividing by a negative. So we have x minus 2y minus 6z plus 15 equals 0. So next we're going to take a look at example 2. We have to find the Cartesian equation of a plane that contains these 3 specific points. So remember that the 3 points are given to be on the plane, points A, B, and C. And for us to be able to define the equation in Cartesian form, it's easier to have the perpendicular to the plane. Recall that if you connect lines AB and BC here, or the points AB and BC, then the 2 lines will intersect each other and form a plane. And I want you to think what can be a vector that is perpendicular to both lines, or the plane that is made by both lines. So that would be the cross product vector, right? So in order to determine the normal, we need to find the cross product of AB and BC. So we'll write in here that normal to the plane would be equal to the cross product of BA and BC. And for this, I'm going to start off by finding the coordinates of BA, because we only have the coordinates of the point, right? And we have for BA, remember that we start from A now minus B, because A is the head. -1 minus 3, -3. And then we have 2 minus 2, that's a 0. And then for Z, 5 minus 4, which is 1. 5 minus 4. Crossing vector BC, so from C we are subtracting B. So -2 minus 3, -5. -3 minus 2, -5 again. And 6 minus 4, which is 2. Now recall that and remember that you can take the cross product of these two vectors, but you can take the cross product of any two vectors that you can form with the points A, B, and C. So let's start cross producting. So -3, 0, 1, -3, 0, 1, -5, -5, 2, -5, -5, 2. Draw the line, and now we're going to go down, and then we'll go up. So let's get started. So 0 times 2, 0i. We have -5 times 1, -5j. We have -3 times -5, 15k. -5i. -6j. 0k. So 0i minus -5i, that's 5i. -5j minus -6j, that's going to be positive 1j. And 15k minus 0k is 15k. So therefore, we're going to say the normal will have the coordinates 5, 1, 15. So in order to determine the equation, which is in the form ax plus by plus cz plus d equals 0, we're going to use the coordinates of any point on this plane. And I'm going to use b because it's all positives. So we have x equals 3, y equals 2, and z equals 4. And the normal will have the coordinates 5, 1, 15. And from here, we're finding the value of d. So we have 5 times 3, 15, plus 2, plus 60, plus d equals 0. So d equals 75, 77 negative. Therefore, we'll say that the equation will be 5x plus y plus 15z minus 77 equals 0. And voila. Oops. This would be the scalar equation of this plane. So I hope that this all made sense, and I'm going to continue with the next examples in the next video. Thanks for watching. Bye for now.